Welcome to Section 8, Lesson 5. The difference of squares is the cleanest factoring pattern in all of algebra. It takes two perfect squares connected by a subtraction and produces two binomials that are mirror images of each other. The whole technique fits in a single line. The formula is a squared minus b squared equals a plus b times a minus b. Read it from left to right. Any expression that looks like a square minus another square factors into the sum and difference of those two square roots. The pattern requires both pieces to be perfect squares and the sign between them to be subtraction. The geometry is intuitive. Think of a big square of side A with a smaller square of side B cut from one corner. The remaining L shape has area A squared minus B squared, and when you slice and rearrange it, you get a rectangle of width A plus B and height A minus B. Same area, two different ways to write it. Today's two examples cover the basic application and a case where the pattern applies twice in a row. The double application is the standard trick on x to the fourth minus a constant, and it lifts straight into many later sections. The pattern is a squared minus b squared equals a plus b times a minus b. Both sides represent the same quantity. The right side is the factored form. The geometry below is an area proof you can hold in your head. Picture a square of side. The total area is a squared. That single number sits at the top corner of the diagram, and the entire square is what we are starting with. Pure a squared, nothing taken away yet. Now cut a smaller square of side B out of one corner. The piece you removed has area B squared. The remaining shape is an L, and its area is exactly a squared minus B squared. Two squares, one big, one small. The difference between them is what we are trying to factor. Slice the L along the diagonal of its waist and rotate one piece into place. The shape becomes a rectangle. Its width is a plus b, its height is a minus b. The area of that rectangle is a plus b times a minus b. Same area as the original L, two ways to write the formula. That equality is the difference of squares pattern. Factor 20, 5x squared minus 49. The first job is to recognize this as a difference of squares. Both pieces need to be perfect squares of something, and they have to be connected by a minus sign. 25x squared is the square of 5x, 49 is the square of 7. The minus sign between them is exactly what the difference of squares pattern requires. So A equals 5x and B equals 7. Rewrite the polynomial in the squared form. 5x squared minus 40. 9 equals 5x squared minus 7 squared. That makes the matching to the formula explicit. Apply the pattern. A plus b is 5x plus 7. A minus b is 5x minus 7. The factored form is 5x plus 7 times 5x minus 7. Two binomials, one with a plus, one with a minus, and the work is done. Example 2. Factor x to the fourth minus 16. The polynomial does not look like a difference of squares at first glance, because x to the fourth has a higher power than x squared. But x to the fourth is the square of x squared, and 16 is the square of 4. So this is a difference of squares in disguise. First application of the pattern. X to the fourth minus 16 equals x squared squared minus 4 squared, which factors as x squared plus 4 times x squared minus 4. We have two factors now, but one of them is itself a difference of squares. The factor x squared minus 4 is a clean difference of squares. X squared is the square of x, 4 is the square of 2. So x squared minus 4 factors as x plus 2 times x minus 2. Apply the pattern a second time on this factor. Combine. The full factorization of x to the fourth minus 16 is x squared plus 4 times x plus 2 times x minus 2. The factor x squared plus 4 does not factor further over the real numbers. There is no real number whose square is negative 4, so x squared plus 4 stays exactly as it is in the final answer. 3 takeaways for the difference of squares pattern. They cover the formula, the recognition test, and the limitation. The formula is a squared minus b squared equals a plus b times a minus b. Memorize it. It shows up in nearly every section that follows. Whenever you see two perfect squares connected by a minus sign, the factorization is one line of work. Both pieces must be perfect squares, and the sign between them must be subtraction. If either piece is not a perfect square, the pattern does not apply. If the sign is plus, the pattern does not apply. Check both conditions before reaching for the formula. A sum of two squares, a squared plus b squared, does not factor over the real numbers. There is no pair of real binomials whose product gives back a sum of squares. That is why x squared plus 4 in example 2 stays unfactored in the final answer.